Today we get to talk about the most important tensor. We spent all this time introducing the idea of tensors in a flat space-time, introducing a new playground for tensors, more generally manifolds. And now we're going to tell you about the metric tensor. So the metric does a lot for you. In general relativity, we're going to talk mostly about the metric when it comes to tensors. I guess the stress-energy tensor might be the second most important, but the metric is what tells you how to compute lengths and times of things. It tells you about the motion of test particles, the Earth going around the sun and all that, or the corrections, that Einstein found for Mercury's motion around the sun due to general relativity. That comes from the metric, right? It replaces the gravitational field phi. It tells you about the causal structure of the space-time, and it tells you what you mean by locally non-rotating. If you think about it, you're off in space and you want to say, okay, I'm not in a rotating frame because your accelerometer doesn't show anything. Well, translating that mathematically involves the metric. So it really does everything gravitational for you. If I give you a manifold and I give you a metric, you can do physics in the presence of gravity. You need to add your own physics, your equations you're interested in, but you do those on this manifold with metric. And after we introduce the metric, of course, we'll talk about all that physics. So here's what the metric is. It's a symmetric rank 0, 2 tensor. And so its components are g mu nu. Now, we called the metric eta in flat space-time, and eta is going to continue to be an expression for the metric in the special case of flat space-time in Lorentz frames. If it's not flat space-time in a Lorentz frame, then we're going to call it g mu nu. So we'll mostly be writing g mu nu. It also has to be non-degenerate, meaning its inverse exists. So we can define the inverse metric, and we're going to use g upper mu nu for the inverse metric, and this is the only tensor where upper is going to mean inverse, just like in flat space-time. For all other tensors, upper and lower are related by factors of the metric, like we introduced. So the inverse metric, by definition, then, is the metric where g upper mu nu, g lower nu alpha equals, that's not what I meant, find the undo, equals delta mu alpha. Okay, so you can think of that kind of like a matrix multiplication. An up index and a down index summed together is logistically the same as a matrix multiplication, and then this is the identity matrix. So that's why we call this the inverse metric. And then there's a funny notation. So the strictly correct notation would be that the abstract tensor G is given by its components g mu nu times, or rather summed in with, the basis 1 forms in the coordinate basis that we're dealing with. But for whatever reason, we always write, instead of g, we write ds squared. It's a tradition that everyone adheres to, and I will too. It basically makes no sense. There's no ds. There's just ds squared, which is really the abstract metric g. But that has survived from Euclidean geometry, where ds is a little infinitesimal length. And then we drop the, always drop the tensor product symbol, because it would just be too annoying. And so it's the second equation that we'll be using. So when I give you metric components, I'll almost always write ds squared equals something, 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 and you can infer the metric from that. So for example, the Minkowski metric, we had been writing ds squared equals eta mu nu dx mu dx nu, which we'd been writing as minus dt squared plus dx squared plus dy squared plus dz squared. So that's the same thing as, eta mu nu equals minus 1, 1, 1, 1 with zeros off the diagonal that you're familiar with. But, there'll be other metrics. Another example. So, I don't know, what's a good metric? Here's one we'll meet later in the course. It's the Schwarzschild metric. 2gm over r dt squared plus 1 minus 2gm over r inverse dr squared plus r squared d theta squared plus sine squared theta d phi squared. So, we will study this in depth later, but when we write this, it means that you infer that, okay, gtt is equal to minus 1 minus 2m over r, 2gm over r, yeah. grr is now 1 minus 2gm over r inverse. G theta theta is r squared, and g phi phi. So, and if you had off-diagonal terms, they would look like dt dr. There's a factor of 2 that shows up because of the fact that you need a dt dr term and a dr dt term, and there are 2 of them. We'll cross that bridge when we first see cross terms in the metric. Most of the metrics we'll deal with will be diagonal. But for example, when you have rotation, like a rotating star or a rotating black hole, it tends to introduce time-space off-diagonal terms that you can't eliminate. All right, so metrics can look arbitrarily complicated if it's a complicated gravitational field, or just if you've changed to some complicated set of coordinates. But it's natural and true that near a point P, you can, or let's say at a point P, we have lots of freedom to choose the coordinates for our metric. It's a 0-2 tensor. We have 4 functions of 4 variables to make a coordinate change, to change the components of our metric tensor. And so we can use that freedom. A proof is sketched in the book, but it's very natural, at any point P to set any metric to a diagonal metric with some number of 1s, some number of minus 1s. Now, you can't, this is the same as the number of positive and negative eigenvalues. You can't change that. So the number of these is called the signature of the metric. So number of plus 1s versus minus 1s is the signature. So you could give that by specifying 2 numbers, or sometimes people specify the difference between them. In our case, the signature is always going to be minus 1, 1, 1, 1, just like the Minkowski metric. So the Minkowski metric, everywhere in space, in a Lorentz frame, the components are diagonal minus 1, 1, 1, 1. More generally, for a curved so-called Lorentzian metric, this is the name for a metric with that signature, at any point you could put it in the Minkowski form with a coordinate transformation. And that's a natural thing to do to characterize what kind of metric you have. And when we get to curvature, we're going to interpret that as finding a coordinate system where the metric, its local flatness is very manifest because it looks just like the metric of flat space-time. Yeah, if you're in n dimensions, yeah. So for us, we'll have 4 dimensions, and our signature will be 3 plus 1s and 1 minus 1.
Drawing significance to the order. So
No.
top you wrote positive first. Okay.
Yeah, it's a convention. So we put the negative first. You could also flip the whole thing by a sign. That's a common particle physics convention. So you'd have 3 minus 1s and 1 plus 1. Yeah.
Is there a case that we care about in the like a physical sense that is not 3 and 1 negative?
Yeah, if you look on a submanifold, so for example, if you wanted to talk about an instant of time, that would be a spatial submanifold. It would only have 3 dimensions. And then its induced metric, the metric on that slice, would be Euclidean, plus 1, plus 1, plus 1. And sometimes if you look on funny surfaces like null surfaces, you get metrics that actually have a 0 in there. So they're not really metrics in the sense I've defined, but we still think about them in that way. But the metric of space-time will always have this signature. Yes?
Is there occurring geometries where you can't locally do this, or can you do
No.
this locally?
Yeah, you can just write out just take any metric as I've defined it, a 0-2 tensor, assume it has arbitrary components at a point, and then solve for the coordinate transformation that at that point will put it in this form. And you can just see that there's always such a coordinate transformation. There's no physics in it whatsoever. It's just characterizes the different, well, I shouldn't say there's no physics in it whatsoever. There's no notion of curvature yet. It's just characterizing the different kinds of metrics that we could have, and ours will always have this signature so that it can properly represent lengths and times in the way it did in special relativity. And as soon as we define curvature, we'll call this making the local flatness manifest. But for now, it's just a property of metrics. Was there another question? OK, so the metric finally gives us the dot product. It's the thing I told you to forget about because gradient is not a dot product. Gradient is really a contraction between a one form and a vector, and so on. Now that we have a metric, we can talk about a dot product. So I won't actually use that notation too much, but we should say it. So an inner product on vectors. So I really won't be writing this much, but we could say v dot w is g mu nu v mu w nu. I don't know, maybe I'll write it somewhat. We'll see how the class goes. But this is very different from the dot product that you're used to. This is not positive definite. Okay? V dot w can be negative. And we'll actually do an example shortly. Sorry, v dot v can be negative. So a dot product, right, normally is positive definite in the sense that if you plug a vector into it twice, you get a positive number, which is 0 only if the vector is 0. So now, yeah, so thank you for that correction. So of course, v dot w could already have been negative if they were just anti-aligned. But now v dot v can be negative. That's a Timelike vector. And the other thing that can happen is v dot v can be 0 even when v is not itself 0. And that's just a null vector. Okay, so these two properties make the inner product, usually it's called indefinite, as opposed to positive definite. So not positive definite. And this is just what happens for Lorentzian signature metrics, and it's just something to keep in mind. Comments, questions?
Is this just an artifact that G has negative components
Yeah.
in a Euclidean metric?
This wouldn't happen if if the signature were all pluses, you wouldn't have this. But for our Lorentzian, yeah.
I was going to ask, is there a case where you have all negatives in your
That would just be a different convention for,
Okay.
so if we were working in the plus, minus, minus, minus convention for our space-time metric, then our metric in this room would be negative definite. And when we computed lengths with it, we would say, oh yeah, the length is really minus v dot v. You know, somewhere the minus sign shows up. We just have it in the when we compute times.
So is that for all Timelike vectors, it's negative, and for all norm?
Yes, that's the definition of Timelike vectors, is that its norm is negative.
And if it's not negative and not 0, it's not Timelike?
Then it's space-like, sure. Okay. So let's complete the list. So v dot v positive is a space-like vector.
So for like physical paths, you actually expect it to be?
The tangent vector to a massive body is Timelike. So has negative norm. Yeah. And tangent vector to a photon is 0 norm, so null. But this is just any vector. It could represent anything. Yep. What? What kind of geodesic? Yes. What about it? Okay. All right. So let me show you some nice things about the notation. So we already had an example about you know, how you can just kind of coordinate transformations are easy. Right, so the example last time where we changed the components of a tensor in the dx mu, dx nu notation, and it was very easy to get all the components at once just following the little rules of how you're supposed to manipulate those little d symbols from, you know, calculus and implicit differentiation and all that stuff. So that's one nice thing about the notation. Another nice thing, another example, so here's example 1. Example 2 is finding the induced metric on a submanifold is easy. So let me explain what's meant by that. So let's do it via an example with the sphere. So suppose I'm in Euclidean space. Let's do a Euclidean metric. Not worry about time. So we've got, you know, x, y, and z. And suppose we have a sphere. That's supposed to be centered. And suppose we want to know the metric of the sphere. So we'll define the sphere as an embedded surface in Euclidean space. And we'll ask, what is the metric of the sphere? Now, what does that mean? Well, remember, a metric is a 0-2 tensor. So it's a map from two vectors to numbers. So the three-dimensional metric is a map from three-dimensional vectors to numbers. And the metric on the surface of the sphere should be two-dimensional, so it should be a map from vectors on the surface of the sphere, which are two-dimensional, to numbers. So if we just restrict our three-dimensional metric to only take vectors tangent to the sphere, we get a two-dimensional metric. And that's the induced metric of the sphere. So our notion of length in three-dimensional space tells us our notion of length on the sphere. And yeah, in this case, this is a common example if we do want the metric on a submanifold. So I'm giving it to you in 3D space. I've now told you what length is in 3D space by writing the Euclidean metric. And I'm going to show you now a nice way to get the induced metric on the sphere using this notation. Okay, so the first thing we want to do is describe the sphere nicely. So let's say the sphere is the surface r equals 1, where r is square root of x squared plus y squared plus z squared, or we could write it as x equals r. Is it cosine? Cosine? No, sine. How do I not remember this? No, isn't z r cosine theta? Sine. It's sine. Yeah. No, and the correct convention is the physicist one, obviously. R sine theta cosine phi. Y equals r cos theta. Oh my gosh. I don't know why I suddenly blanked on that. Sine theta sine phi. Z equals r cosine theta. Well, you would be wrong.
But also, I use this convention now.
Okay. There is no, come on, there's no difference between theta and phi. Give me a break. It's just a convention.
Oh, yeah.
Greek letters. So we just follow the notation. So the first thing we're going to do is convert this to spherical coordinates. So we have x, y, and z. We're going to need dx. So dx is going to be dr sine theta cosine phi plus r cos theta d theta cosine phi plus r sine theta minus sine phi d phi. And we're going to do the same thing for dy, the same thing for dz. I think there'll be a homework problem where I ask you to actually go through this. You just sort of plug in and collect terms and do a bunch of trig identities. It's not very hard, but it's not worth doing it in class. So you do those three things, you plug it in, and then you will find Sure. Why not? For the mathematicians who stumbled into the class and don't know the universal physics convention. It's just a convention. I'm not saying it's better, but it fortunately is universal within physics. There is no disagreement. So.
I'm not suggesting a change. I'm just saying that,
Okay, there you go. So theta is the angle from the z-axis, and phi is the clockwise, according to the right-hand rule, with the thumb along the z-axis. Yeah.
As long as you remember that, I'm going to get a girl.
Okay, so you plug that in. And actually, the ranges are important. You should think of the ranges as part of the coordinate transformation. There's also going to be a homework problem where the ranges are very important. So I'm glad someone mentioned that. So the point is, when we introduce these coordinates, we need to make sure that we're covering, or we at least want to cover the whole space where x, y, and z can be any number. And so to do that, we need to let r be between 0 and infinity. We need to let theta r equals 1 is the surface. Right now I'm just getting the metric of Euclidean space in spherical coordinates. 0 is less than theta is less than pi, and 0 is less than phi is less than 2 pi. And notice I made these all strict less thans. I mean, there are just points that are not covered by these coordinates. And we always take our coordinates tab open.
So do we not actually cover the entirety of the sphere?
Yeah, we miss the poles, and we also miss the origin of space in spherical coordinates.
Well, I think we also miss a line along the...
Yeah, but that really never matters in practice. I could write less than or equal to here, and the formulas would all work because we're always using 2 pi periodic functions. It's really the one at the pole where things start blowing up. And you'll see that actually when I write down the metric. That'll be a very nice thing to do. So when you go through this, collect terms, then what you'll find at the end of the day, in fact, I'll copy down the original Euclidean one just so we can see them next to each other. You'll find that this same metric is given by dr squared plus r squared d theta squared plus sine squared theta.
Wait, wouldn't the parentheses be on the other side of...
Did I do wrong? Something wrong?
The parenthesis should be
Oh, yeah.
So you have like a d theta squared d phi squared. Right?
Yeah, of course. Thank you. Okay, so you'll find that. And you can then read off the metric components. So it's GRR equals 1, G theta theta equals R squared, and G phi phi equals R squared sine squared theta. Right. And so one way you can see that we don't cover the poles is, well, you could take the determinant of this metric, for example. So that would be one way to see there's a problem. So the determinant is just now the product, and so that's going to be r to the 4th sine squared theta. And you see that this equals 0 at the poles, right? So theta equals 0 or pi. And that's a problem because if a metric has 0 determinant, if matrix has 0 determinant, you can't invert it. So no inverse. And so you see there's a coordinate singularity at poles. And we emphasize it's a coordinate singularity. You all know that because you have a nice picture of three-dimensional space. And we started with a perfectly smooth metric. We made it singular by changing coordinates. But it was perfectly smooth. So the singularity has to do with just our bad coordinates at the point. Later in the course, we're going to have metrics that look singular, and we're going to have to discover that they were actually coordinate singularities as opposed to real singularities, and that's the history of black holes, basically. So let's see explicitly with the inverse metric, as long as we are doing this example thoroughly. So we could, of course, compute the inverse metric from the formula. It's a diagonal matrix. So the inverse is just diagonal so G upper RR equals 1, G upper theta theta equals R to the minus 2, and G upper phi phi is R to the minus 2 sine minus 2, if you like, 1 over R squared sine squared theta. And again, you can see the problem that it's blowing up, right? Blows up at these poles. And you can also see the problem at r equals 0. Okay, that's a bit of a tangent, but useful. So now I've shown you how the notation helps you quickly get the metric in new coordinates. And now we started all of this by asking for the induced metric. And here's where things are really, really slick. So the induced metric, all we do is we set r equals 1. That's natural, because that was the definition. But what's dr if r equals 1? Well, according to that's not what I meant to write. According to the calculus notation, dr would be 0. It's constant on the surface, right? And so if we do that, then we will find the induced metric. This is on the sphere. We just take our expression, so ds squared equals, dr squared, dr is 0, and r squared, that's 1, d theta squared plus sine squared theta d phi squared. So the metric on the unit sphere is just d theta squared plus sine squared theta d phi squared. So take my word for it that this is correct, but if it's unsatisfying and you want to be very formal about induced metrics as the restriction of the metric to the surface of the sphere and the restriction of the inputs to the metric to tangent vector surface to the sphere, the appendix of Carroll on maps between manifolds and pullbacks is very nice and clear, and you can read it. And you can check that this notation does give you the correct induced metric in that sense. I would definitely recommend computing with this notation. So if you want to find the induced metric on some surface, and there'll definitely be a homework problem exploring that for the cone. So you'll see how the induced metric of the cone as an embedding has an issue, but as a manifold itself is totally fine. And I definitely would recommend doing the calculation in this notation. All right, I'm going to make a stronger claim. And the stronger claim is that not only can I take a metric g mu nu and find coordinates where it equals a to mu nu at a point, I can also use the coordinate freedom to make the first derivative of the metric vanish at a point. So I can set g mu nu equals eta at a point P. Set g mu nu is eta, and I can set del alpha g mu nu equals 0. Okay, it's again, if you don't like all these assertions, you can go look at the argument of the book. It's just a matter of writing out a whole bunch of equations and showing that there exists a solution according to the theory of PDEs. Yes?
And so we're saying that that's 0, but I think, didn't we have something where, like, we can't always say that
The components of this thing do not define a tensor. But in a coordinate system called local inertial coordinate system, I can certainly write the equation. So these equations hold only in the local inertial coordinates. Okay, so thank you for that question. That hopefully,
At 1 point.
yes, at P. Mm-hmm.
So the first one, I guess, is just like the g equals nu thing, it's just saying locally it's flat.
We will add those words to it when we define curvature, yes.
Okay, so I don't need to prime it.
Yeah. So another way of saying this is we could approximate the metric near P as g mu nu is approximately a to mu nu plus order coordinate differences squared. The first order deviation from flat vanishes. And that is actually a much stronger statement because metric is kind of like Newtonian gravitational field. We'll make that more precise. Motion of test particles in Newtonian gravity is related how to the Newtonian gravitational field? If I give you phi, how do you compute the gravitational force? Take a derivative, right? Yeah, it's the first derivative of the gravitational field. So the first derivative of the metric is going to be our Newtonian forces. And what we're seeing here is you could always pick coordinates such that the first derivative of the metric is actually 0. And that's the equivalence principle. You can't tell you're in a gravitational field. You can always find a frame adapted to your lab where there's no gravitational force at all. Okay, so this mathematical statement actually has the equivalence principle in it. Does that make sense? G is like phi. Force is like grad phi minus grad phi. So it's sort of saying gravitational forces are a coordinate effect. So when we get to curvature, we're going to find out that the curvature is the thing you can detect locally. That's going to be sitting in this delta x squared term. There's going to be a big tensor called the Riemann tensor that sits here. And that's the locally measurable effect of gravity. Questions? The equivalence principle idea? So the equivalence, one of the versions of the equivalence principle we talked about is that in a sufficiently small region of space, using only gravitational experiments, you can't tell whether it's, quote, really a gravitational field or just some effective acceleration. So we interpret that as saying there's really no such thing as a gravitational force minus grad phi. That's just not a useful concept. We argued that using the equivalence principle. And I'm just telling you that g is playing the role of phi. And so setting the derivatives of g to 0 by a coordinate transformation is expressing the idea that we could just change, that we can't detect the local force grad phi. It depends on our coordinates, yeah.
So you can do like a coordinate transformation so that the first derivative disappears, but the higher order derivatives.
They won't disappear, that's right. And the next term, we will characterize this term in terms of a tensor called the Riemann tensor, which has to do with curvature in spatial surfaces, and so we call it the curvature of space-time. Four indices, yeah. We'll get there fairly soon. I'll write that in too. Curvature will go here when we define it. Now, the reason I introduce these local inertial coordinates now is they're very useful for translating special relativity laws to general relativity. And this is incredibly simple but very subtle, and I do give a homework problem on doing this, and it's a one-line homework problem, yet lots of people miss it. So here's the version we'll talk about in class. Let me give you an example. So suppose we want to know how fast something is moving. Okay? So how fast is the rocket moving? You know, according to us. So where's some frame? This is the question. So in special relativity, you set up your Lorentz frame. You say that's us. And how fast is the rocket moving? That's dx dt in your Lorentz frame. Now, in general relativity, we're not going to have a global coordinate system where the metric is eta mu nu. At best, in general, we'll have this local eta mu nu. So we want to use that local eta mu nu and use the coordinate-dependent laws in special relativity and make them look coordinate-independent. So let's draw a picture. So here's us. And then the rocket has some other time-like world line. Okay, and when we're separate from the rocket, we don't answer the question, how fast is the rocket moving? That's a local question. Okay, if the rocket is moving, way off in a distant galaxy cluster, we're not going to say how fast it's moving. We'd have to wait 100 million years just to send light to it and do some kind of experiment. This relative velocity is local. Okay? And so we're really interested in this point P here. Okay. So the way we do this, at P, go to local inertial coordinates. Okay, so g mu nu is equal to eta mu nu at P. And now we say, okay, let's use our Lorentz freedom, right? We still have local Lorentz boosts and rotations and so on. Let's use our Lorentz boost to make this our rest frame. So choose these, let's call this LIC so I don't have to keep writing them. So choose LIC to be our rest frame. So what's meant by that is, well, now in these coordinates at this point P, u mu is 1, 0, 0, 0. Okay, so that u will be our for velocity. So that's u mu. And for the rocket, it will have its for velocity, let's call it w mu. Now, we're just in special relativity. We want to write our for velocity of our moving body. Well, there's a general form for the for velocity of something moving, right? It's the gamma factor times 1 comma, velocity. This is what we mean by velocity in special relativity. If you like, it's the definition of relative velocity. Right? These two are important. We're in our rest frame, and so if we work in the components where our for velocity is 1, 0, 0, 0, then the other person's for velocity takes this form. Okay? So these are our coordinate-dependent laws in special relativity. These depend on the Lorentz frame. If we boosted, of course, the form of our for velocities would be different. But we can notice something, that if we dot these together, so I'll use the notation since I promised I wouldn't, u dot w, which is the same thing as a to mu nu, u mu w nu, is equal to minus gamma. Right? Just because we put a minus sign in the time components multiplied together, and there's zero space components there. Exactly. We need to do one more step first. We have to use that at p. G mu nu equals eta mu nu. So at p, that's actually G mu nu, U mu, W nu at p. But now, these are just tensors that are well-defined everywhere. Everything's independent of coordinates, because we're using the actual space-time metric, a 0-2 tensor, the actual for velocity of us, and the actual for velocity of the rocket. Okay? So what this means is the relative Lorentz factor between us and the rocket is gamma equals minus u dot w, where I really mean this one here with the metric. Okay, so this is a perfectly tensorial expression. So this is a good coordinate invariant expression that will work even in the presence of gravity. So if I had given you that Schwarzschild metric of a black hole I mentioned earlier, and I had you in a rocket ship orbiting at some radius, and I had another rocket ship flying into the black hole past you, when the two rocket ships are close, I ask you, what's the relative velocity? It's actually a very easy calculation. All you do is you take the metric, and you take the two for velocities, and you do the dot product, and you're done. Yes?
So like near P, we said that eta mu nu is just equal to change, right?
At P.
Yeah, but we don't change the for velocities, right? It's just when we are converting from...
This all should be at P as well. Relative velocity is only defined at a point where you're both there.
So we are going from flat space-time to curved space-time, right?
Well, this formula, we derived it that way, but this formula holds in curved space-time at any point P where there are two world lines, two time-like world lines, intersecting at that point. And it tells you that, someone on one of those world lines who went and measured the velocity, ignoring gravity, right? This is just local at a point. You can't detect gravity, right? So ignoring gravity, that person near that black hole just measures the speed of the asteroid going by her or whatever. And the result of that measurement mathematically will be given by this dot product between the four velocities. So you can use GR to predict what that measurement would be. And I guess I should say relative velocity then is just however it's related to the Lorentz factor, square root of 1 minus gamma to the minus 2. But the Lorentz factor gamma is easier to think about because it has the nicer formula. So we usually talk about the Lorentz factor between two bodies, not the relative velocity. Yes?
Is u and w the same in both the local flat space-time and curved space-time, or will they
So you'd have a world line in the curved space-time with a tangent vector u at every point along that world line, and another world line with a tangent vector w at every point. And those are just curved space-time things that exist over the whole world line on the manifold. And then at the one special point where they agree, we could introduce, where they're intersecting, we could introduce a local frame. And then we'd say at that special point, in that special frame, u becomes 1, 0, 0, 0, and w becomes gamma 1, comma v. But in practice, you would never do that. That was a trick of the derivation. I did that for the derivation in order to get this, in order to get this formula here, down here, that doesn't refer to any special frame. You could just do that in whatever coordinates you're working in.